Hello, this is Engineer Rodolfo Ocati from Iloilo City, Haro, Iloilo City, Philippines. Today we have this 5-span beam, and we will solve this by 3-moment equation, and this is series of 10 lectures. The equation is it is a very long expression, but I will explain this. This is moment on the left. So we consider 2 span at a time for a 3-moment equation. Consider only 2 span. We have so many span. So the first expression is the moment on the left times the distance. Then the second expression is the moment at the center of the 2 span, or B. Twice of that. Then the sum of the 2 span, first and the second span. Then the third moment is the moment on the right of ABC. Then this constant is constructed by this. This is first one. Okay. Then area 1, the first area, the area of this, we will compute this, the area, then the corresponding centroid A1 is from the left. So we have this first span, the origin must be on the left. For the second span, the origin must be on the right. Okay. So the area times the corresponding distance of each of these geometric figure, then there is a corresponding centroid of this figure. For the second span, 6 over the second span, then area, then the centroid must be on the right, because this is the second moment by part, and it is called as the moment by parts on the right. So the right moment by part, the centroid of which is from the right. Okay, we go direct to the how to find this value. Now consider AB as a simple beam. The reaction RA is total load divided by 2. Split this into this RA and RB. So 4 times 4, 16 divided by 2. The reaction of RA is 8. Then the reaction 8, make that as a moment going to B. So 8 times 4 is 32. Okay. Then due to this uniform load, we create this. The moment of this uniform load to B is 4 times 4 total load, 16 times the distance of 2. So 16 times 2 is 32, minus 32, it is going down. Okay. Then for this, consider BC as a simple beam. The total weight is 4 times 6 is 24, divide that into 12. Then make the 12 a moment to C, pivot that to C. So 12 times 6 is 72. The same is true with the uniform load. It is going down, parabolic, total load is 4 times 6 is 24 times 3. The centroid of 6 is 3. Is minus 72 also. Now how to make this? Consider a simple beam CD. We have a couple only. So this moment 72 and minus 72 is 0. 32 and minus 32 is 0 because the moment at the support for a simple beam is 0. Now we will construct this without solving the RC. Down below here, due to the couple of 16, the moment at D is minus 16. Then right away we can conclude that this is also 16. The sum of these two must be 0. Okay, so no need to compute for the reaction at C. Reaction at C is a dummy force. To find this, the 108, the reaction of D, uniform load of 16, total load is 6 times 6, 36, divided by 2 is 18. 18, then make a moment to E. The reaction at D is 18 times 6 is 108. The same is true with the uniform load down below here. The total load is 36 times 3 is 108. On the right, consider this as a simple beam. The total load here is 6 by 4, 24, 1/2, 6 by 4, 24 divided by 2 is 12. Okay, the reaction at F, 1/3 of 12. Reaction at E is 2/3 of 12. 1/3 of 12 is 4. Reaction at F. Then multiply that by 4 to make a moment. It is 16. Then right away, this is also 16 because these two must be 0. Okay. So we go now to the substitution to this equation. Now we consider always 2 span at a time for this 3 moment equation. 2 span at a time. The first one, moment on the left, moment at A is not equal to 0, but the moment is 10 by 2 and it is negative or minus 20. Then L1 is this first span of ABC, 4. Then twice moment at the center of ABC or moment at B times the distance first and the second span, 4 plus 6. Then moment of the right of ABC or moment at C times span of 6. Then the constant of the moment by part, this one. So 6 over first span, 4. Then area of triangular, 1/2 32 by 4, distance from the left. So 2/3 of 4. The origin of the moment by part on the left must be on the left, the origin of the distance. The origin of the moment by part on the right, moment by part, is on the right here, going to this origin. In our case, the first span, the origin is for a triangular loading of 32 by 4. The centroid is 2/3 of 4 here. Then the lower part, moment by part, is a parabolic. So it is 1/3 of 32 by 4. Then distance is from here up to here is 3/4 of 4. Okay, this is the left moment by part. The right moment by part, the constant is this 6 over L2, or 6 times the area of the triangle, 1/2 72 by 6, times distance on the right as 1/3 of 6 from here up to here, 1/3 of 6. Then the lower part is parabolic, 1/3 72 by 6. Then the distance is 1/4 of 6. 1/4 of 6. Then equate that to 0 because we have no settlement, either A, B, or C. 0. Then simplifying, 2 times 10, 20 MB. 2 times 10, 6 MC. Then the constant, we have 80 here as minus on the left of the equation, 80. This constant is 64, and this constant positive 216. Positive is higher than negative, so these three are positive. Transfer that to the right side of the equality and it becomes a minus 200. Copy this, copy this. We have two unknowns, moment at B, moment at C. Constant is minus 200, and this is equation 1 for span ABC, 2 span at a time. Then another equation, BCD. Now you will notice that in a 3 moment equation, the unknowns are the moment. Here in this beam, we have 5 unknown moments. Moment at B, moment at C, moment at D, moment at E, moment at F. They are all 5 unknown moments. To solve this, we have to create 5 equations. The first equation is that we have already created the first equation, and that is 2 span at a time, A, B, C. This is 2 span. Next equation is that we create by considering the span B, C, D. This is the second equation. Third equation is the 2 span C, D, F. Fourth equation is consider D, E, F. And the fifth equation is we consider E, F, G, where G is an imaginary span. F, G is imaginary span, because in a fixed end, we have another redundant unknown here, the moment here on the right. Then we create this to make a 2 span beam. So the last 5th equation is 2 span is E, F, G. Okay, so we have to have 5 equations. We have one equation for ABC. Next equation is BCD. Consider this as BCD. Now substitute to the original equation M1 L1. First moment of BCD, M1 L1 or 6 moment at B, twice the moment at the center or C, twice. Then the sum of 6 and 6, L1 plus L2. Then moment on the right, D times the L2. The span of BCD. CD is the second span. Then the constant 6 over L1 for BCD. The first span is 6. Then moment by part, the area is 1/2 72. For this triangle, the distance is from the left 2/3 of 6. Then at the bottom, parabolic, this is 1/3 of 72 times 6. The distance is 3/4 of 6. This is a parabolic, 3/4 of 6. This is the first moment by part. The second part, the constant is this. For the second span of BCD, the 6 over second span is 6. Then for the area, 1/2 6 times distance of 1/3 of 6. 1/3 of 6 minus the rectangular area 16 by 3. Then distance from the right is half of 3 is 1.5. Then equate to 0 because there is no settlement. And simplifying, 6 MB, 12 times 2 is 24 MC, 6 MB, and this first constant 216, the second constant is plus 24. All positive, transfer that to the right, it becomes negative. Again, we have this. Usually moment at B is negative. At the moment at the support is usually negative. Moment at C is also at the support, and B also negative. These three are negative, so this must be negative. This comprises the equation 2. We have now 3 unknowns here. Then the next two span is CDE. CDE. First span, second span. Okay. Then substitute M1 L1. The first moment on the left of CDE is C times 6. Twice moment at the center or at D. Then sum of the two spans, 6 plus 6. Then moment on the right of CDE or E times span 2 or 6. Then the constant 6 over L1 for the first span or 6. Then the area is, okay, CDE. This is triangle 1/2 16 by 6 times 2/3 of 6. The origin of the first span on the left must be on the left, or from here up to here, the centroid is 2/3 of 6 minus this rectangle, the area is 16 by 3, and the distance of the from the left is 3 plus 1.5 from here up to here. 1.5. This is for the left span, the first moment by part. The second moment by part of CDE, this one, the second moment by part is 6 over L2 or 6. Then the area is 1/2 108 by 6 times 1/3 of 6. Then minus 100, 1/3, 108 second degree parabola times from here up to the centroid. It is the second moment by parts. On the right of CDE, the origin must be on the right, or 1/4 of 6. Okay. Then equate this to 0. Simplifying 6 MC 12 times 2 or 24, 6 MA. Then the constant here, minus 24 for this, then 324 for the second constant. 324 minus 24 is 300. Positive, then transfer that to the right, becomes minus 300. So this is equation 3. Okay, next we have consider this two span DEF. D is F. First span, second span on the right. Then okay, moment on the left, M1 L1 is moment at D times 6 plus twice the moment at the center of DEF, twice moment at E times the distance of sum 6 plus 4, then plus moment on the right of DEF, moment at F, and distance of 4. Then the constant of the moment by part, 6 over the first span, 6, then 1/2 108 times 6 times distance on the left as 2/3 of 6, then minus 108, 1/3, 108 times 6 times distance from the left as 3/4 of 6. This is for the left span. The right span, the origin must be on the right. This is now the computation of the second constant, 6 over L2 or 4. 1/2 16 by 4 times from here to here 2/3 of 4, then minus 1/4 of 16 by 4 times distance from the right as 4/5 of 4. Then equate that to 0. Simplifying, we have 6 MD, 10 times 2 or 20 MA plus 4 MF. The first constant is 324 second constant is minus 51.2. This is too small compared to this first 324. It is because this is a smaller area compared to this. Then this is positive, transfer that to the right of the equality, it becomes negative, minus 375. And this is now the equation 4. Equation 5, consider span EFG, imaginary G. Okay, substitute moment on the left of AFG, moment at E times 4 times twice the moment at the center F of EFG. Center is F, moment at F times 2 times the sum of the two span, 4 plus 0. Then the moment on the right or G is 0. Then the constant on the left is 6 over 4 times 1/2 16 by 4. The origin is on the left, 1/3 of 4. Then down below, this is third degree parabolic, 1/4 16 by 4 times the distance here on the left, so 1/5 of 4. Then the moment by parts on the right is 0. Then equate that to 0. Simplify this. For ME, this is 8, 4 times 2, 8 MF. Then we have only one constant. Then move that to the right of equality. It is negative for 4.8. And this is equation 5. Now we have 5 equations, and we have 5 unknowns, B, C, D, E, F. Moment at A is already known. It is moment at A is minus 20. So we start at B. So this is the solution of the 5 equations. Maybe you are wondering how to solve this. Okay, I have prepared here my tools for the moment. This is using the Gauss-Jordan simultaneous equation. Okay, compute. This is the solution. Same answer, 8.099. Moment at C, 6.33418. Then minus 65633 minus 17412. Then positive 3106. Okay, can you trust this? Okay, suppose I will change this to, okay, that's all for the solution of the moment. I will just prove to you that this is a program. So I will change this to 8 and compute. This will change the solution. Compute. Okay, so everything is changed if I change this. I will change this to 12. Compute another solution. I will change this to 20. Compute. So it changed to another answer. go back to 6, then this is previously I think 6. I will check the first equation. 20, 26, then 200, 20, first equation 20, then 6, then 200. Wow, 20, then 6, then 200. I will compute. So the same as this. 8.09935. Everything the same. If the substitution of this numerical constant are correct, then we will have a correct roots of the equation. Now you can change this. Suppose I will make this 3 equations only, so I will edit the data so that I can change this to 3 equations. Edit data, I will make this as 3. Okay, so this is just an example. We have this numerical coefficient, then we have this, then compute. We have also corresponding root of the equation. If I change this to 24, there is another solution. Okay, I hope you got this, how I got these values. Okay, now solving for the reaction, we have now all moments are given. I want to solve RA. So cut section at B, just look on the left side of B. Moment at B here will appear as clockwise, -8099 here, -8099. There is a moment at B on the right, clockwise. Then it is due to, okay, moment on the left is due to 10 and uniform load of A and also RA. Actually, the moment on the left is counterclockwise. It is in this direction. Moment on the right is clockwise. These two moments must be equal at B. So whatever the moment created by 10 and the 4 uniform load and the reaction here, equate that to the moment on the right as -8099. So this is our how to solve the RA. RA is unknown. So moment at B is equal to this 8.0997. RA times 4, unknown RA, minus 10 times 6 minus the uniform load of 4 by 4, centroid is 2. Then this is the moment on the left. Moment on the right is -809973. We have one unknown RA. Solving for this using calculator, RA is 20.9751. Okay. Then solving for RB, cut section here. Then consider only on the left as given here. When we cut section here at C, we can see the moment at C as clockwise. The value is minus 63342, the moment on the right, and the moment on the left here are here. No, the direction, the sum of this moment is actually counterclockwise of all the sum of this moment on the left. Then moment on the left equated to moment on the right. Okay, so moment on the right is minus 63341. Okay, solve for RB. RB times 6 plus the reaction at B given as 20.9751 times 10 moment at C. Then concentrated of 10 times this distance as 12 minus the uniform load of 4 times 10 times 5. This is 10, and equate that to the moment on the right, minus 6334218. Then we have only one unknown, RB, and it is equal to 17.3192. Okay, solving for RC. Okay, again we cut section at D, consider only all the forces here or all the moment on the left, equate that to the moment at D as clockwise here. Moment at D is equal to minus 6563395. You will note that the moment at C is also 63342. They are almost the same or equal, but they are different. They are almost the same because of the 6 and minus, but they are different. Moment at D is minus 65633. Okay, moment at D is different from moment at C. Okay, so RC is unknown here. RA and RB are already solved. RC is unknown. Okay, we sum up all the moment at D. So RC times 6 times reaction at A 20.9751 times distance 6, 6 and 4. This is 10 and 6 or 16. Then RB is also known as 173192. 173192 times 6 and 6 or 12 minus the concentrated load of 10 times, this is 6 and 6 or 18. Then uniform load 4 times 10 times the center of this 10 is 5, so 5 plus 6 is 11. Centroid of the uniform load 11. Then due to this couple, it is negative. Notice the loadings are negative. It is with respect to D, the rotation is counterclockwise, then the rotation or moment is counterclockwise. Moment of couple 16 is also counterclockwise, so this is also minus 16. No distance, it is already a moment. Then equate that to 6.56, the moment at D. We have only one unknown. Solve this by calculator. RC is 14.3342. Okay, So reaction RA, RB, RC are now known. We have now on the right 3 reactions. Okay, to solve RF, we cut section at E. Then consider the right segment EF. We cut section at A. There is a moment at A as counterclockwise equal to 17 minus 17 for 1 to 2. Then moment on the left is for minus 17. Moment on the right is the sum of all the moments on the right, including the moment at F. Moment at F is positive 0.3106, positive 3106. So moment at E, okay, moment at E is minus 17 for 1 to 2, and it is counterclockwise. Okay, solving for RF, moment at E, RF times 4 minus 1/2 6 by 4 times 1/3 of 4. From here up to here, 1/3 of 4. Plus the moment at G as 3.106. And equate that to the moment at E, or minus 17 for 1 to 2. We have again one unknown, RF is equal to minus 1.1296. It is going down. RF is going down. Now solving for RE, we cut section at D. Okay, consider only the right segment of on the right of D or DEF. When we cut section at D, there is a moment at D of minus 6.563. There is a moment of minus 6.563. Okay, the sum of all the moment on the right, unknown RE, okay, times distance of 6 minus the reaction at F minus this one, or minus 1.1296 times 10. Then moment at F, positive. Rotation is like this. Rotation of RA is like this, counterclockwise. Rotation of moment at G is counterclockwise. So positive 3.106. Then minus this uniform load 6 by 6 times 3. 6 by 6 times 3 minus this triangle 1/2 6 by 4 times distance from D 6 plus 1/3 of 4. 6 1/3 of 4. Then equate that to minus 6.563395. Again, we have one equation. RA is equal to positive 32.9377. So we have now solved RA, RF. We have only one unknown, RB, left. Again, cut section at C. Consider all the moment or forces on the right of C. And when we cut here, there is a moment counterclockwise at C of minus 6.3342 moment at C. Moment on the right of C is this. Then we will equate this with the moment at C. Okay. Our unknown is D. So solving for RD times 6 plus 32 reaction at E, 329377 times from C. This is 3 and 3 is 12. Then minus reaction at F, minus 1.1296 times this times from C. 10 and 6 is 16. Then moment at F, positive 3.106 positive, minus the uniform load of 6 by 6 distance from C is 3 here, 3 plus 6 is 9. Then the triangle 1/2 6 by 4 distance from C is, this is 12 plus 1/4 of 1/3 of 4. 12 plus 1/3 of 4. Then we have a couple left, plus 16. Okay, plus 16, and equate that to the moment at C, minus 6.3342. Then we have one unknown RD. Solving for RD, this is 13.5634. You can check these answers. If you add RA, RB plus RC plus RF plus RE plus RD, and these 5 reaction, 6 reaction, it must equal to the sum of these vertical forces, excluding the moment because this is not a force. Okay, that concludes the solution of our problem for this beam. We have solved the 5 moments, then 6 reactions. I hope you understand because this is good for you to design, to make a design. Now, given the all the forces, surely this will close and the shear diagram must be closed. This is the shear diagram. Force on F is negative. It must be close here to 0. Then the shear moment diagram will look like this. The moment at F is positive. The values of this is under the topics of the strength of material, and I don't want to explain how to solve the shear and moment diagram. Okay, it's up for you to check also this. Then I have here a problem for you to solve. This one problem, the figure is the same, the figure almost the same. The values are changed. Concentrated load, instead of 20 I make it 20 instead of 4. uniform node, and 6. I make it 6 and 8. Then a couple of 16, I make it as 26. The distances are the same. Then dimension are all the same. The answers for the 5 moments are this. I hope you can solve the simultaneous equation for the 5 equations. Then the reaction, the 6 reaction are this. Okay, that's conclude our 10th session of the 3 moment equation. I hope you enjoy this, and please subscribe my video. Thank you and good day.